Okay, I think we can start off with our chapter 1. Chapter 1 is specifically looking into a structure, satellite technology, structure, and in general, this is also applicable for, as I've mentioned during the introduction, it's also applicable for generally spacecraft. Okay, a craft which is going to be in space. So let's start off with the general rules. Now, unlike other structures, you can compare maybe automobile, you can compare aircraft. Space structures are a bit more specific and a bit more, I would say, critical, because you can't get to touch it or you can't get to maintain it when you start flying. Like aircraft, you can actually do aircraft maintenance. Car, yes, you can actually send to the workshop, but unfortunately, the satellite, once you send it to space, you can't actually bring it back and start repairing it. There's no such thing. So if you look at our issues, basically, the crucial issues that we have always, reliability and safety, is extreme. If you ask me something, rocket science is very, very difficult. And that is the reason reliability and safety issues, number one. Once you have only one chance, you cannot fail. Failure is not an option in space because it's going to cost you a lot of money and a lot of time. You can't just go and buy a satellite like today. You go to maybe a shopping center and you get a satellite, and then tomorrow you are going to fly a satellite. It's not like that. It's not like buying a car. It's not even like buying an aircraft, I would say. So it is every time it's tailor-made. And every satellite has a very, very unique mission. And this unique mission is what determines the actual satellite design is. So satellite design, again, is always driven by the mission of the satellite. So if you look at it, so reliability is very important. So which means that, okay, I have a mission, a very low-cost mission, maybe 2 years to fly. Or maybe I have a mid-range mission, 5 to 7 years to fly. Or maybe I have a long-term mission, maybe up to 20 years to fly. So if you look at it, you are going to do this without any maintenance, a maintenance-free system for maybe 2 years, a low-cost mission, maybe 5 years to 7 years, or maybe long duration, maybe 15 years mission. How to do that? Now, I always invoke this example. Assume you have a light, we have lights here. Can you imagine if you switch on a light today, and then you come back maybe 10 years later, do you seriously think the light will be still on? So it's very, very challenging. So light is so simple, but can you imagine the whole system is actually going to work for 15 years or 10 years? You own your car today. Let's say after 10 years later you come and actually sit in the car. Is it possible? And that is satellite. So, keyword here, safety factor. Our safety factors are much higher. We always play safe compared to any other engineering field. Okay? Optimization of mass. You can't simply build what you want because every single kilogram is so expensive. A typical kilo will cost you probably up to about 25,000 US dollars, can be up to about 50,000 US dollars to bring it up, including the insurance. So a kilo, let's say a liter of water, you can even afford a liter of water for $25,000. That's space. That is satellite. So you can't simply do whatever you want, because it's going to cost you the mass, and don't forget the volume. Now, optimization of mass is just because of that, it's expensive. Second, limitation of volume is because of your launcher, the rockets. The rockets are quite almost standard. So you need to fit your satellite into the rocket, not the rocket fits you. So it's different. So you need to design a satellite which can sit inside the rocket. You can't have, that is the reason most of the time you see the satellites are almost cubical in most missions. It is is not round in shape, it is not, different kind of shape. No, the shape doesn't change much because of the launcher that we have. Then you have a mechanical load. Now this is very critical. Why mechanical load is that, remember, before the satellite can even operate, the launcher has to carry the satellite into the orbit. Now when you have seen rocket launches, you will learn in fact rocket launches in your subject. But again, when you start actually launching, you can see the load, so much of load. And the load is not only being transferred to the structure of the rocket, but also the payload. The payload here is the satellite. Okay, a rocket will have a rocket engine and all the stages, and the final will be the payload. Payload can be anything. Can be your satellite, can be a warhead, anything you can call a payload. Okay, that is a mission. The mission driven. So your satellite also goes through the heavy load when you are launching. So it is a heavy task, not only to design a satellite when it is going to operate, but also to survive during the launch time. Okay, if you look at human's life, there are ups and downs, right? There are good times and bad times. For satellite, the bad times are indeed, known bad times are indeed during the launching, because that's the most stressful, especially for the structure. So it is so many precautions that we should take. Then production, of course, production is you need to have a track record. Nobody wants to send an equipment which doesn't have a track record. All those systems must come with a track record. That means it has flown maybe 5 years or 10 years in space. Then you want to actually acquire and put in your satellite. If it's not proven why you want to actually fly it, assume that one system failed, it is going to be a catastrophic failure. Usually any system fails, it is going to be a disaster in making. So we cannot afford failures. Failures is not an option in this design work. Method for requirement. Our philosophy is worst case design. The worst can happen. What is the worst can happen? So you design accordingly. Take no chances. That is the design philosophy. It is not just by putting a safety factor 1.5, 1.2 that you are safe. No. Sometimes you need a safety factor of 100%. For example, you have a system A, and you have to have another system A identical to it. Backup system in satellite. That is the difference. So it's going to cost a lot. Cost volume, cost mass, cost money, cost complexity. Yes, suppose. Safety failure analysis will have to be done. Power saturation of equipment, that has to be taken care. When we talk about our power systems, we are going to discuss about power saturation and what kind of bus actually we can use and how to basically dump those saturation and what kind of profile that we are going to have. We will discuss that also. Special material, not all material you can carry. Remember, if you put the steel, it's going to cost you volume, sure. It's going to cost you also mass. You can't simply put steel. You need to put something light, but yet it's very strong. So the options are not too many. Typically used, you can see you have titanium, Kevlar, carbon. These are typical materials. So composites are also walking in slowly into the space frames. Okay, you have composite frames already. Typical ones that you have we've been always talking about today. If you look at the actual satellite's body, it looks like one sandwich because it has a sandwich structure. And if you open the sandwich structure, you can see it's just like a honeycomb. It's like a honey web. So honeycomb, so to say. So you can see that. So there are reasons why we have this kind of structures in satellite. Load analysis is extremely important so that we can survive. We can survive the launch, for example. Okay, that is very, very critical. Now, again, continue. Production. As I've said, you need to have that record. If you don't have a record, please don't buy any space equipment. If they say that yes, we have done the best equipment, best system, best power system in the world, and there is no proof of it has a flight time in space, don't buy it, or rather don't require it. You can't take any chances. But assume that system is not version 5.0 maybe. It's only version 1.0, but it has served in space maybe 20, 30 years. You may want to pick that because you are very, very sure it's going to survive. Production and quality control, extremely important. We will actually, when you do the satellite testing, you will be also exposed to some important testings that we do in order for the satellite to survive. Environment conditions, it is not easy to live in space actually. Space looks very beautiful, but when you go and start living in space, it's very, very difficult. It's very hot, it's very cold, full of radiation. I think if you are not practically protected, especially with your clothing gears, I think you are counting your days. Human body just can't survive in that kind of very harsh environment. So it is not a very easy thing. When human can't survive, it doesn't mean that equipment that we design can also survive. Same rule applies. So we need to take care of all those important or rather critical conditions into the design factor. Procedures. So we have a very strict procedures. So we can't simply bypass the procedure. When you bypass the procedure, that means the design of worst case is in compromise. When it's compromised, disaster immunity, as I've said. Testings. You test everything and anything before you send to space. Okay? Components must be tested, material must be tested. Now, that is the reason you look at material, you have a screw, for example, a rivet. You see aircraft, yes, we have that also. A rivet which is used in aircraft cannot be readily be used in spacecraft. Not necessary. It has to be space qualified. A material used in car cannot be readily used in space. It has to be space qualified. So our materials are all and components should be space qualified. Even a simple plaster, a sticker. Let's say you have when you do thermal control, there is a layer is called krypton. Gold color layer. So in order to, it's just like a paper. So when you want to actually start gluing it, you have actually stickers. That stickers also has to be space qualified. Everything has to be space qualified. Performance and function proof must be done here. You must know it's 100% working before you are setting it up. Configuration control, you must be there. Configuration control means is this. When you know functionality of each and every equipment that you have, there is no company in the world producing all this equipment of a particular spacecraft. No, no such thing. Even in the car, it's like that. Even in an aircraft, it's like that. In aircraft, you see Airbus is a aircraft producer, but the engine is actually produced by someone else. So it's just like that. So in order for us to have a full configuration, we must do a global test so that all these systems coming from a different vendors are in harmony, respecting your design. That is important. Good mechanical properties. Dynamic compartment is important. Why dynamic compartment is important? As I said, during the launching time, your satellite is almost going up and down. This is getting excited because of the lift that launcher is giving. So the dynamic compartment of this is extremely important. Okay? Now I will invoke for this dynamic compartment. What is important, I think, you have learned in dynamics, even specifically in vibration, the mass and spring model comes into play here. Okay, I will explain maybe later when we do the exercise about how we can pick the mass and spring model to equate with our satellite. How can we do that? Rigid, it has to be very rigid. Otherwise we break. Remember, when you start actually putting a very high force during the launch, it will break. It won't break the launcher, but it may break the things inside here. Okay? Because of a high load. Stable and thermoelasticity. As I told you, very extreme condition, very cold, very hot. So cold, hot, I think human will get sick. So likewise, you will have a temperature, very high temperature gradient. It should not actually be sensitive to those temperature gradients. That's very, very important. Now, space environment, as I said, it is not a very easy environment. 15 kilorad to 25 kilorad dose is basically a radiation dose. All those equipment, especially electronics and electrical equipment, must survive that amount of radiation. 15 kilorad up to 25 kilorad have to. Otherwise, you can never survive. The higher that you go, let's say you go near the sun, let's say it's a sun mission, this gets higher. 15 kilorad, maybe for a very low Earth orbit, yes, you can survive. Very low Earth orbit. Okay, there are three. If you learn space mechanics, you will know there are types of orbit: low Earth orbit, medium Earth orbit, then geostationary orbit, which is higher compared to all the other two orbits. So there are altitudes of all these orbits. If you look at the temperature gradient, now look. When you learn space mechanics, you also know that any rigid body will fly around. Let's say it's Earth oriented. So it will fly around planet Earth. They will go into the sun phase, collect energy. Maybe that is how we are supposed to design our satellite. When we see sun, we know that when we have a photovoltaic cells, we can harvest energy from sun. So maybe when we go into sun, we can harvest energy. Then when we go back planet Earth, there will be a eclipse. So therefore, look at the temperature gradient. Negative 40 degrees. It's not easy for you to survive. Huh? And look at the extreme temperature, 60 degrees. I think about 40 degrees you can have heat strokes already. Yeah? 45 to 46 degrees you can have a heat stroke. Yeah? So this is a 60 degrees. 101%, I think you will be affected. Yeah? You walk out, heat stroke is just waiting. So it's a very extreme condition. Now, this is very certain. I'm just giving you a very, very rough estimation. That is the launching cost. If you have a very good launcher, then you pay a very, very low amount of insurance because it's a very reliable launcher. But if you have a launcher which don't have much of a track record, then the insurance will be higher. So when the insurance will be higher, per kilogram it actually goes high. Okay? Now, typically you can expect you will pay around about 25,000 per kilogram. Now this is just like this. If you have about 200 kilogram or 300 kilogram of satellite to launch, this would be the actual price. But if you have only one kilogram of satellite, basically, what the very small satellite can be even about a kilogram. That will cost you, well, I would say about 150,000 euros, or $1,000. So it is not like proportional. This I'm giving you a general satellite range. The smaller amount that you spend, the send is more expensive. The bigger mass actually you have, the more mass you have, you can actually have a better pricing. It's normal. When you buy something in bulk, it's cheaper for you. If you buy only a single product, it's going to be very expensive. So that's general rule. Alright, now look at the material choices that we have. Space structure materials, very, very typical, just like in an aircraft. Aluminium is quite well used, in fact, in aerospace industry. So you have aluminium plates, you have rivet, these are quite typical. Now why? And look at the specific rigidity. I think all of you know for aluminium, specific rigidity. E is a modulus Young, okay? Modulus Young over the actual density. This is actually the specific rigidity. Now in space, you want to have a good rigidity. Remember, we have defined that. You must be stable, you must be very rigid, so that you will not break. Kevlar and carbon, This is actually quite familiar, rather quite common material to use because they are stable, and the mass is also very attractive because lighter compared to even the aluminium. Carbon matrix, these are all already composite. If you look at carbon matrix, ceramic, they have a very high thermal properties. So if you look at all these applications, so assume that now high thermal properties they have. If you want to actually, there is also a mission of Earth observation mission, for example, where you have cameras to look on certain areas in the planet Earth. So camera is very, very sensitive, especially the instruments are very sensitive to thermal expansions. So for those kind of areas or those kind of components, the selection of material should have a very, very good buffer in terms of thermal properties. Then typical composite materials are also coming in. I've given you all these examples. Look at the thing is that it has a very good specific rigidity. Rigidity is quite high compared to even the aluminium. This is important. It's more rigid. Composites are more rigid compared to even the metal, for example, aluminium. So the good thing about composite is lighter, it's stronger. So it is quite effective already. So it's quite popular in recent years. In fact, a lot of small satellites they are already having a composite structure already. Yeah. Typical material which I've discussed just now. So if you look at it now, tensile strength, sigma. Okay. Now if you look at it, look at our aluminium. Very low. Very low. Titanium is high but very expensive. Normally in divergence, especially in the propulsion system in divergence, titanium is well used. But you look at fibers, composites, look at that. Very, very high in terms of strength. So it is very, very strong. But let us look at the density. If you look at the density, it has a lower density also. So which means that the mass also would be lower compared to the actual steel or even aluminium. So that is the reason why it is quite attractive nowadays to combine not only the metal or aluminium but also together with the composite. Now, if you want to looking at all these selections, you have many. I've mentioned many materials. What I have given you here, these are certain components that you can find in the satellite. Now, in a satellite, basically, when you find certain components, they should have certain performance required. Central tube. What is central tube? Central tube is that if you have a big satellite, central tube is that where the whole, all this equipment will be embarked to it, and it is just like one pillar. Okay? Not necessarily it can be a tube, it can be even a plank, just like that. So, but we call a central tube. So it has to hold most of this equipment. It should have a very high rigidity. It must be very strong because you end up holding the other equipment. Optical structures, very, very important. Optics. When you have a camera is very, very sensitive to temperature. So the thermal resistivity must be taken care of. Okay. Solar generator and disk. Now solar generator and disk. If you look at it, this can be a particular wheel which is rotating in the satellite, maybe to give you some sort of torque, for example, or some sort of momentum for stabilization. So it's the disk. Solar generators can be also photovoltaic, okay, and this also refers to your parabolic disc, for example, antenna, etc. It's outside. But for inside, this can be basically your reaction wheels, for example, just for stabilization purposes. Now, even in that note, it's very, very important to have a very high rigidity because they will be stable. Outside, you're very stable. Inside, you're also very stable. Okay? Thermolysis is important outside. Inside, remember when you see when we do thermal control, we will see. If you see inside the satellite, you will have an average temperature about 10 degrees, not more than that. You should maintain that. If you look at all the list of equipment that we have, there is a temperature range. We should provide at least about 10 degrees. So you can imagine how tight is that temperature requirement. Tanks. What tanks is that? Fuel. We have some fuels for some satellite. You will see, because when the satellite comes with the propulsion system, you must have fuels. So we will see what kind of fuels is there. But tanks can come in a very, very high specific resistance. Specific resistance is nothing but sigma over rho. Okay, strength over rho. Thermal protection, low density with respect to material fraction. So these are basically carbon-carbon. These are typical composite material for thermal protection. We will also see what kind of thermal protection material that we are going to use in thermal component or thermal control system. And we will cover that in the chapter. Short revision. I would like to remind that you have been exposed to already deflection and how to calculate deflection when you have a beam, when you have a force, how to calculate the deflection that you have been exposed to, how to calculate natural frequency also you will have been exposed to. This is in a strength of material, this would be in vibration, or sometimes it's in dynamics. So please do revise these two terms so that you know what we are going to do. All this you have been exposed to. All this you have been exposed to. Okay? It's just a revision. Please revise that. Okay. Sandwich structure. Now, how to build a box? You must have a bar, then a bar, and then you must have a wall, right? So the bars can be simple. Let's say it's a low-cost mission. Simple. Let's say the bars are all aluminium bars. Okay? We have aluminium bars, aluminium bars, aluminium bars, aluminium bars. Now we need the wall. The wall typically we say that is a sandwich design. Sandwich design means what? If you cut the wall, you will see like it is like a honeycomb. Okay, it's like a honeycomb. So if you cut the wall, so wall is here, wall. If you cut it, then you will see that the honeycomb is there. Okay, so it's just like this: wall, then you cut, then you can see the honeycombs. Just like that. Okay. So when you see, let's say a box, you see, you won't see the honeycomb outside. You will see only a plate, but behind the plate is a honeycomb, and after the honeycomb is another plate. That means it's just like a sandwich. Okay, plate, middle, honeycomb. Why? Let's do the design justification. Now let's say 3 cases. 2 plates, right? That's why I say plate, honeycomb. So now I want to tell you, okay, fine. I don't want honeycomb, I just want 2 plates, just like that. Okay. Poor bending stiffness. We will explain afterwards. It's a poor bending stiffness. Problem. I need good stiffness. But here you have a poor bending stiffness, which means that it may be like this. We don't want it. Okay? B. Middle low density cause fall. Now this is honeycomb. This is honeycomb. This is what you see here. This is honeycomb. Okay? Bending stiffness increases. Okay? Bending stiffness increase. Now let's EID that. Keep in view. KC on a block. If you look at it, it's just like a chunk of mass. No layer, just one block. Okay? What exactly will happen? If you look at it here, if you zoom in clearly, the mass is going to increase. Can you afford it? In space we can't. We don't want mass. Okay? This is light. But unfortunately, poor bending stiffness. If I embark that, it will be like that. Yes, of course. A layer of wall, put it together. This is what happens. So you want the wall, what you put a huge block. Then it will not do this. Do not bend, but heavy. So what do? We do honeycomb. So what exactly happens? It actually increases the stiffness. The reason when you look at it purely why it increases the stiffness is because let us look at the formula. Bending stiffness for isotropic and bending stiffness for composite. Isotropic is where if you look at 3 dimension x, y, z, they are all equivalent. That means the mechanical properties are equivalent. That means what? For example, metal are isotropic material. Composites are not. You can have a different strength in all directions. That is composite. But metal, all directions you will have same because it's isotropic material. So the formula for bending stiffness is for isotropic. E is Young's modulus. I think all of you know. I is inertia. Okay. And here is Young's modulus. I inertia over 1 minus nu. Poisson ratio. Okay. Poisson ratio. Now, if you analyze this, this formula, why is it that honeycomb or sandwich design gives us a better stiffness? It's just because of this height. When the height increases, inertia increases. When the height increases, you look at it, the inertia will increase because of the calculation of the inertia, formulation of inertia. Okay, maybe I will give you one example for you to explore. So that is the main reason. If all of them have the same material, that means your modulus, Young's modulus must be the same, all same material, but only the design is different, right? So in this case, the height of, when the height changes, it gives a very good inertia. When inertia is high, given a constant modulus Young, bending stiffness increases. Likewise, inertia increases, bending stiffness increases. So that is the reason why composite material, another sandwich structure or honeycomb structure is very, very popular. Structure calculation, static analysis, and you can say static analysis, you will be exposed to finite element method. Well, you have done static, you have done all those calculation forces and all those moment, you have done that. That is useful, but when you want to work in maybe 3 dimension scenario, it could be difficult for hand calculation. Finite element analysis is excellent. So having that, then what you can have basically, you can end up calculating the strength, sigma. You can get sigma using finite element methods for a complex geometry. Yeah. Stress calculation is submitted to quasi-static load. Now, in this field, I would say in a stress analysis field, in order for us to model, just like when you are launching, let's say, launching a rocket, we have a satellite beam, and we want to emulate that exactly like the real situation. It's very difficult because the rocket movement also depends, and there is also gravity in play. So we are almost modeling it like a real case, and we can use something we call quasi-static load. That means it is almost, it is not static, but it is almost like a dynamic case. In order for us to model the dynamic condition. So static analysis, but we can actually extend that into almost like a similar dynamic case. Static load. Buckling, I think all of you know. Now, we have a central tube, remember? You keep on embarking heavy loads, let's say putting equipment on top of it, putting antenna on top of it, it might buckle. Buckle means this. So, static analysis is important. Yeah, that one. Okay? So, it is very, very critical in terms of the strength. And if you look at dynamic analysis, just now we did a quasi-static, but if you are not capable of performing dynamic analysis, quasi-static you will do. But again, a good approximation will be dynamic analysis itself. So here, finite element method can be applied. This is very useful for maybe your elective subjects. If you are going to learn a finite element method, it's good reason being you can actually have the satellite structure model in finite element. Then you can actually look at the static part, static load, static stress, stress inside. Then due to static condition, and then you can look at actually the dynamic part. Okay. Now, whenever we consider dynamic analysis, eigenvalues, I think all of you know, in dynamics or other vibration to be specific, always you calculate lambda. Yeah, if you can remember. Okay, that is the eigenvalues. Okay, that you have. Then there is also something called the mode shapes. Why? Because when you start launching, it is just like the structure is going up, doing this. So it will have basically a frequency, or you say a natural frequency. If you meet the natural frequency, then it may break. So you got to be careful. Okay, that's the first part. Second, it will have mode shape. What is the mode shape? Assume this is a launcher. This is rigid, let's say it's rigid, not shape this. But when very high acceleration and load, the structure tend to do this. And this we need to know. If it's too much, then it will break. Any structure for the matter. This happens not for static. In mode shapes, you don't do for statics. You only do for dynamics because there is acceleration. When there is a motion, there you can reduce the motion. Okay? Now, so this is basically excitation at the base of the satellite. I told you when you want to embark rocket, embark the satellite, base of satellite is cold. This happens. This excites. Okay, this is very, very critical. And based on that, other survivability of other subsystems inside the satellite also can be determined. So the satellite itself is going through difficult times or difficult conditions. Equipment itself also does that. So we need to be careful with this, and which means that we need to also test all those equipments inside the satellite, not only the satellite. We must qualify them also, because they are subject to this movement. Okay? Now comes into this calculation. Now, if you look at it, this is the only calculation that you probably have been exposed to, acoustic calculation. We don't do acoustic calculation for most of the things. Maybe from acoustic, not in terms of for dynamics. Now, this acoustic calculation is needed. Reason being, when you launch a rocket, it is very, very loud. The engine sounds are very, very loud. Due to the engine sound, the structure is going to get excited. That means what? It is going to affect the structure because of a loud sound. Now, if you could remember, let's say in opera, the people sing, the ladies sing in a very high pitch. When in a very high pitch, the acoustic is actually has a very high decibel, right? What exactly happens? Let's say you have a glass, you can even break the glass. Then we have seen that. That is the exact thing that is happening to the satellite. When the rocket makes a lot of noise, it can break the structure of the satellite. Simple. Just like the singer sings very, very high pitch, can also break. Okay? So watch that. Now, follow me on this. Octaves. Let me define octaves. What is octaves? Octave is a frequency band at F such that the future F, which is I plus 1, the future F, is equivalent to 2 of the current F. That's what it means. Okay? But the delta of the current F itself is defined as current F, the delta of current F is current F over 2 or O square root of 2. Now, remember, the frequency band is normally we can calculate, or rather we can actually, or given, that depending on the launcher. How the launchers can provide you this, they start the engine, they record the acoustic. They can tell you what is the pressure that you get. Okay, this pressure, what pressure is this in terms of decibel for each and every band? That means, look at the singer just now. The singer has sung a song in a very high pitch. There is a amount of decibel. When you speak, you have decibels, right? Music in decibel, you can calculate that. So that pressure breaks the glass. So we need to know that. This is a logarithmic scale. So let me define this. The pressure, I need to know what is the pressure so that I can be safe. Okay. So the pressure I define for each band is nothing but, based on the reference pressure that I have, this is given normally, this is measured, this will be given, Pascal. PO is always the reference pressure, you'll be given basically what you have tested this noise, and this will be basically the P effective, that is the effective pressure that you have. It's basically square of this effective pressure, which can be written also as W. W is basically band power spectral density. PSD, we can measure this. When you run the system, when you have a noise, we can actually measure the PSD. Once I measure the PSD, I know practically how much of this pressure in terms of the noise that you are going to have. So, what I need to know? I need to know what is my WPP, for example, PSD. I know this reference pressure, then my frequency. When I have this, I should be able to tell you what is the pressure of this particular noise, right? When I know this particular noise, I know at what frequency it is actually operating, and I have to make sure my equipment is going to survive that noise. It is just like this. Assume you want to fly a satellite, you bring the satellite and give to the singer and ask the singer to shout, or sing rather, and see whether it's going to break or not. But before I bring that, what I'm doing here is that I am measuring the singer's pressure. The actual pressure in terms of decibel. In terms of decibel, I measure. So I don't have to have the singer anymore. I can have another engine outside there and emulate the decibel that singer is going to give me. That's it. So it is exactly like the actual condition, like during the launch. Okay? Now, if you look at, in rocket technology, you should learn this also. If you look at a rocket, there is always 4 pillars. Especially if you look at Ariane. These 4 pillars are basically to mitigate the actual noise, the noise waves. To mitigate that, there is another complex simulation. Okay? That will actually dampen. So, with all this is calibrated. So, the value of reference pressure, the value of frequency band, the value of power spectral density, it varies from one launcher to another launcher. It means that from one singer to another singer is different. Okay? Alright. Now, once this is done, power spectral density is clear. Effective acceleration is what you want to do. Because effective acceleration is what the final product that you need to know. Reason being, we know what is the acceleration of the rocket, right? Effective acceleration is, you can see how many G is this equivalent pressure. Equivalent pressure in terms of decibel is how many G actually. It's just like this. You are singing and it breaks. Okay? But actually, in rocket it's not singing, rocket is flying, The difference is that. So, when the rocket is flying, what exactly it does? It has an acceleration, right? So what I need to do, I need to have another maybe equation that tells me exactly what is the relation between the power spectral density due to the actual decibel, the pressure, how it is going to be equivalent to my effective acceleration. That's why it's called effective acceleration. So it is equivalent to this much of acceleration. So what it means that if you calculate your acceleration, effective acceleration is more than actually the acceleration of the rocket, you are in trouble. It should be very much lesser. That is very minimal. Actually, it doesn't get excited. But then if it gets excited, it's going faster than the rocket. Imagine yourself. What it means, but it doesn't happen. Let's say your payload, your satellite, your rocket, satellite, this guy is flying faster than the rocket. That's what it means. So technically you will break, right? If you fly same acceleration with him, you will be just at the mountain. If you fly, if your follower, that means that you have a slightly lesser, he will be pushing you up. But if you have more, then you are going to break away from him. So you cannot have more. So that's what it means. So again, I'll redefine this effective. We will do a calculation for you to know. You have natural frequency. This is clear. This will also be given from each. It varies from each and every launcher. Then you have a resonance, basically amplification, and this is nothing but 1/2 zeta. Zeta should be given. Zeta is basically damping. How it actually gets excited. So this the launcher will provide all these data for us to plug inside here and to look at the actual effective acceleration to ensure that we are safe. Typical acoustic qualification. Let's say for RN5. Okay, look at that. This gives you all those decibels. Okay. Now, this is basically your frequencies and practically all the decibels given, right? So for particular frequency, you should not, when you start actually doing this, when you start actually exciting the structure. Okay, let's say your operation is, let's say here, let's say 500, right? Say 500, let's say. So you take 500, so your operation is actually at 500 hertz, right? 500 hertz is operating. Now, when you start running it, when you do a test, your acceptance levels for sure will be higher than the actual operation. Okay? Now, acceptance is 34, qualification is higher. So this one is what you have. The acceptance level is what during the flight you're going to experience. So what you have to do is that 500, you make sure you do a blast on him. That means you start singing on him for 138 decibel so that he will not break. Make sure it doesn't break. You know for the fact when he's flying, he won't break because he's going to operate at 134. That's what it means. So if your calculation shows that you are at maybe, again importantly, this is not from me, this is also not, this is from the the catalog, the Ariane's catalog. So if you're going to launch a satellite, they will give you this. So you compare basically all your equipment, you do a qualification based on this. Now all this what you see here, these are all can be equipments, you know, and prescribed qualifications that you need to do. Okay, look at that. Now assume that at one particular equipment, let's say you have it here, these are decibels. Let's say you have your calculation shows that your frequency shows here, let's say. This is below 1 to 5, right? You cannot pick 1 to 5. That means your testing should be done here. Okay? Yeah, operation, let's say you're operating. This is a curve. This is a curve of each and every launcher. This curve will be different for, let's say, delta. Yeah? Will be different. Will be different for each and every launcher. So, let's say you have already your operation range. When your operation range, when you have it, so you put here, let's say this is your operation range, pull up, you hit this, right? You cannot qualify here, you have to qualify one step up. That's what it means. Okay? This is operation range of the equipment. And this is the actual condition during the launch that will happen. Look at this. When you are, check, pull up, here. No, my qualification should be here. Just like that. Okay? We will do one exercise, I will give you on this as well. Okay, structure dynamics, general dynamics equation. Familiar with this, right? Vibration. Mass. What is that? Temper. Stiffness. Spring. So it's a mass and spring model. Mass, spring, temper model. Now you would have said that it is 0 here. You would have been exposed to maybe 0. But I'm saying that not necessarily it will be 0. Remember, if I have a force, what force is that? It can be anything. It can actually come and disturb the system. So when you have an A, then A will be null for static condition, but for dynamic condition that will be A. So you add force to it. When you put this into a model analysis, of course there is a derivation I didn't show you here. You can actually come to this equation. Now this equation is a very, very simple equation, but yet a lot of things to understand. This equation is derived from your mass and spring model. But this equation is derived practically to do the model analysis. That means that shape, this shape actually, to avoid this happening. Okay? So you look at it, M is a mass, it is very, very easy. Mass, what mass is that? The structure mass. When you did your vibration or even dynamics, it would have been your mass of the spring, mass of the rigid body. But here will be the mass of the equipment. K is basically the stiffness metric. K is the stiffness metric. When you did the mass and spring model, it's the stiffness of the spring. But here it is not the spring, there is no spring. That is just the structure, so it's the stiffness of the structure. Okay? Now, so X is a vector containing an amplitude just like your mass and spring model. Now, this is important. Lambda is the frequency. This is what you always will find. This is the most important thing. And what is this? Mathematically, it is defined as your X is eigenvector. This is a vector. If you have 3 dimensions, we can write in 3 dimensions x1, x2, x3 as well. That means F1. This is assuming it's a force set. Force 1, force 2, force 3. Force X, force Y, force Z. Fx, Fy, Fz. It's 3 dimensions. You can write it easy. Okay. Lambda is the most important one, is an eigenvalue. Eigenvalue is actually a circular, the square of a circular frequency. So practically, when you have eigenvalue, your omega is what? Square of that. Okay? Square of omega is that. Square of omega is your eigenvalue. So that is exactly what we want to find, because the omega is your natural frequency. And we know the operation of it, what frequency we want to avoid that. So that is how we have to do. We'll try to do an exercise also on this structure testing. Centrifugal, but not all satellites will go through this towards the end. In fact, your last chapter will look into this. We will do a test. Dynamic compartment, you have a vibration device. There is a shaker, can do vibration test for you. Random disturbance, also you can do the same. You see, the difference is that here is random, here is the sinus. So depending, sinusoidal, basically the vibration will be like that. And the random means you can go up, very high, and down. Acoustic, you have acoustic chamber. In acoustic chamber, basically you have to do this acoustic test. These are basically to determine more often than not your telecommunication devices. So then you have a free from all this acoustic disturbance. Shock. This is when the launcher has two stages. So let's say stage 1, stage 2, there is a separation, there's a shock wave. Why is that? Separate. Let's say the booster is going to separate, the spring is going to push the booster. What? Action, reaction. So reaction, there is a shock to the rocket, but also shock to the satellite, but also shock to the equipment inside. So all that is multiple folds. Model analysis, I spoke about it. Thermal compartment, thermal simulator you will have. Yeah? Acoustic chamber is basically all those just like as I said, instead of having a particular singer singing in acoustic chamber, you have to create the noise just like that to replicate the original condition so that you can excite the structure. Alright? With that, we have formally completed the chapter 1, and maybe we can discuss a bit on the exercises.